All right, so in this video, we're going to be looking at the definition of a singular point. This is a concept that sometimes intersects importantly with certain applications in differential equations, such as series solutions. And so we want to be able to, number one, identify a singular point, compare them to ordinary points, and then also we will further subclassify our singular points into regular singular points and irregular singular points, because those kinds of distinctions will have an impact on the kinds of solution methods that we're able to use. Now, the idea of a singular point is essentially that if I have a rational expression like this, a singular point is anywhere where the denominator could be zero, so that the function is actually not defined. So in this example, we'll take our denominator, x cubed minus x. We're going to factor it. And so we're going to find three values, 0, 1, and -1, that are singular points. All other values are ordinary points because they are the only ones that will make the denominator 0. Now, in a function like this, x over sine x, again, we're dealing with some kind of rational expression, although it doesn't have to be a rational expression. Any function where you could get a zero denominator or undefined value is a singular point in this context. So here we're going to set sine x equal to 0. Any multiple of pi will make this expression 0. And so integer multiples of pi are going to be all singular points. So 0, pi, minus pi, 2 pi, minus 2 pi, et cetera, et cetera. They're all singular points. In this example, then we have tangent x over log x. Now, log x is defined for any values greater than 0. So 0 might be considered a potential singular point, but it's not defined really to be 0 at 0. Where log x is going to create a singular point for us is when the entire expression is equal to 0, and that will occur when x is 1, because log of 1 is 0. So that is our only singular point from the denominator. But we're not done, because this entire expression, even on the domain of 0 to positive infinity, we're still going to have other singular points coming up. And that's going to be anytime tangent of x gives us infinity, anytime there is a vertical asymptote. And so, because essentially recall that tangent of x is sine over cosine, and so anywhere cosine can be 0, that's also going to be giving us singular points. So we could think of this function as not tangent over log, but as sine of x over log x times cosine x. So anywhere cosine is 0 is also going to give us a singular point, and that will be at odd multiples of pi over 2. Now, in differential equations, when we're working with series solutions, we prefer, most the techniques are designed to be working around ordinary points where we don't have any points of discontinuity where the denominators are not 0. It helps us avoid complications associated with singular points. So being able to just identify where the singular points are, and so where not to use your general techniques, is also incredibly useful. But it's not always possible to avoid singular points completely. And there may be circumstances where we want to work at this potentially problematic singular point. Now, in order to know whether we can or not, we need one further distinction, which is it a regular singular point or an irregular one? Now, these topics also relate to working with complex variables. We're not going to go into that here, but you will encounter this concept of regular versus irregular singular points in other domains besides series solutions and differential equations, which is where we usually encounter it. At least that's where I've encountered it for the most part. Now, defining a regular singular point is a bit tricky, but an irregular one is easy. Singular points are irregular if they're not regular. So we want to look at the definition of regular singular points very carefully. And I'm defining them here in the context of differential equations, since that is I created this video for that purpose for use in differential equations. So consider the second order differential equation in standard form like so. The point C is considered a regular singular point if all of the following conditions hold. So first of all, C is a singular point for either of these two functions, P or Q. And if I multiply P by X minus C, then the limit will exist. So you may need to use sort of an algebra technique or L'Hopital's to resolve the limit, but as long as you get a finite value for the limit, then you're good. For Q, you would multiply by X minus C squared. And then if the limit exists, then it's again, in all of these conditions hold, it's a singular point, and multiplying P by this factor and multiplying Q by this factor squared, if both of these limits exist and are a finite value, then this is a whole rather than an asymptote. Essentially, it's a whole rather than an asymptote. Then you get a regular singular point and not an irregular one. If either of these conditions fail, so it will be a singular point, but if either of these limits fail to exist, then it will be an irregular singular point. So, and every singular point has to be classified separately. So it's possible for some of them to be regular and some of them to be irregular. It's just going to depend on the specific function. So, for instance, in this third order linear differential equation, we would extend this definition to all of the three functions multiplying our functions of y. We would have p of x, q of x, and r of x. And we would add a fourth condition that we would multiply this third function by x minus 3c cubed. So each time we go down the line, we need one additional factor that could potentially cancel out those singularities. So we need a linear factor on the term one below our highest order, and then a quadratic term on the one below that, two below the highest term. And then if we had a third one, then we would need three copies. And this may help us cancel things, or it may just be the kind of function that they don't cancel. You can, and again, if you have higher and even higher orders, you can continue larger and larger powers in order to try to clear that singularity to see if it's regular or not. Now, regular singular points are defined by asymptotes of rational expressions and zeros of polynomials in the denominator. So if the singular point comes from non-rational expressions like trig functions, multiplying by x minus c sometimes will have no effect, and sometimes they will produce special cases of limits where you can, in fact, convert these to regular points. Otherwise, they will remain irregular. So let's consider our second order differential equation. It's solved for standard form in this expression right here. So p of x is the function that is being multiplied by y prime, and q of x is the function being multiplied by y. Now, both of these functions are undefined at 0 and at 1. They have just different powers. So both of these are singular points. So we want to classify them as either regular or irregular. So for the case of c equals 0, we're going to multiply p by x, and we're going to multiply q by x squared. And so when I do that multiplication, this x will cancel with this x, and it will disappear. And now if I take the limit of this expression, then there is a limit at 0. It turns out to be 3. That's a finite value. That's great. Now, if I multiply q by x squared will cancel out this x squared. I will get this expression. And if I take the limit at x equals 0, I will get -1. That's a finite value. That's good. So that means that this is a regular singular point. Now, if I consider the x minus 1 case, then I'm going to take my p equation and I'm going to multiply by x minus 1. That x minus 1 will cancel one of these x minus 1s. But if I get this result and I try to take the limit as x goes to 1, I'm still going to get 0 in the denominator. This is still undefined. This is still an asymptote. And I don't need to actually evaluate the next one because this is still undefined limit, and therefore it is irregular. Now I can't continue multiply q by x minus 1 squared. That x minus 1 in the denominator cancels. I can now substitute the limit as x goes to 1, and I will get 0, which is fine. But this one, this p, is not giving me a limit, and therefore this x equals 1 case is still an irregular singular point because it failed our test for regularity. So x equals 0 is regular, x equals 1 is irregular, and all other points are ordinary. Now, if we consider one additional example, so again, we have this second order equation in standard form, and now our denominators are x and log x and sine x in our two cases. So p is our 1 over x log x, and q is our x over sine x. Now, p of x is going to be undefined at x equals 0 because of the x, and at x equals 1. And q of x is going to be undefined on all multiples of pi. We can ignore negative multiples of pi because log is not defined anywhere for values from 0 to -infinity. So only positive values of pi will matter. We will consider just one of the multiples of pi, so we'll just consider pi itself, because all of the other ones will behave basically the same. Now let's first consider 0. So when x is equal to 0, we're going to multiply by x minus 0, which is just x, and x squared for the q function. In the p of x case, x and x are going to cancel. We take the limit as x goes to 0, and we get infinity. In this case, when we get x cubed over sine x, then we take the limit. We can simplify this a little bit using a special derivative and a special limit, and we will get 0, or L'Hopital's rule. We will get 0. So here, that's what I did. The limit of x over sine x is the same as the limit of sine x over x, which is 1. And then when you plug 0 into x squared, you do just get 0. But because this 1 over log x isn't defined at 0, this is still an irregular singular point. It's the end of the domain at any case, so that's not particularly concerning. If we test x equals 1, again, we're going to multiply by x minus 1 and x minus 1 squared respectively. And we're going to end up in the factor times p of x case with this expression. And again, we will need to apply probably L'Hopital's rule in order to simplify this. Sine of x is not actually undefined at 1. So the second case, we can just plug in 1, and that's no big deal. So again, we check L'Hopital's rule. This is going to be, if x goes to 1, this is going to be 0 over 0. So we can do it the first time. We apply a product rule, and then we end up with this expression. And then finally, we plug in 1, and we end up with 1. So this actually does turn out to be a regular singular point. And then finally, we look at the same case where we have x minus pi. Okay, we'll just consider one version of pi. If I multiply p of x by x minus pi, I get this crazy expression, but if I plug in pi into my denominator, it's perfectly fine. So this isn't the one I have to worry about. This one is just regular. I mean, it's fine the way it is. It's just some crazy number. But in this case, again, I'm going to multiply by x minus pi squared, and then I'm going to let my limit go to 0. Now, or my limit go to pi. Now, again, I have to use L'Hopital's rule here because I'm going to pi and not 0. I can't use my special limit. But again, I'm going to also have to do a product rule with the chain rule and everything in my numerator. And when I get to this expression, I can then, my denominator is now not 0 at pi anymore. I can plug pi in, get -1, and when I plug pi in up here, I end up with 0 multiplying everything, and I end up with 0. So this one is also a regular singular point because the first term is perfectly well defined at pi, and this one I get a finite value for the limit. And then one last example. We have, again, this second order equation in standard form. The expression p of x will be undefined when cosine of x is equal to 1 or only even multiples of pi. So 0, 2 pi, etc. So if we consider the case of 0, then we multiply 1 over 1 minus cosine x by x. And then we have to use L'Hopital's rule to simplify that. And initially, we get 1 over sine x. When we plug in 0, we're definitely going to still be getting 0. So that's undefined. Cotangent of x is going to give us a similar headache. If we plug in 0, cotangent of x is actually undefined at 0, but I can rewrite it as cosine over sine. And when I plug that in, again, using a product rule, because this is 0 over 0, using the L'Hopital's rule, this denominator will become cosine, and then I can plug 0 in, and I end up with 0 as my limit. Now, the issue here is that this first term is undefined, and so this will still be irregular. And then I can continue on here. I could check in the second expression other multiples of pi to see, again, cotangent and cosine are going to have issues at 0 and any even multiple of pi. And so technically, we would want to check all of those other ones as well. But the results should come out to be very similar.